Okay, what we want to do is talk about the chain rule. The idea is z is a function of two variables x and y, x is a function of at least two variables u and v, probably more, y is a function of two variables u and v, probably more. The idea is, for example, if I let u vary but hold v constant, x changes a little, y changes a little, and that's going to mean z changes a little. So we actually should be able to measure how fast z changes when just u changes a little bit. How are we supposed to do that? Well, like everything else in this chapter, we start with a differential. So I'm just going to write down the differential using slightly different notation because it's going to have to extend. Now what we usually do is we put the partial derivative of z with respect to x, and that's going to go right there, like that. And then I want delta x, like that. And then I want the partial derivative of z with respect to y. And then I want delta y, like that. Now remember, what we want is the partial derivative of z with respect to u. Right? So let me just write this down here. And remember that we use that notation because that's approximately equal to delta z over delta u while holding v constant. So what I'm going to do is take my little equation up here, and this should actually be approximately equal to, and just divide everything by delta u. I'm going to put delta u there, and delta u there, and delta u there, like that. And now if we take the limit as delta u gets close to 0, what we're going to get is the partial derivative we want. Partial derivative of z with respect to u equals zx. Now I can write partial derivative of, well actually let's do it this way. This is the partial derivative I want. You can see that came from the fraction, but more often than not in this context we'll be rewriting this as zu. They do mean the same thing, but we had to use one to find it and one to use it. Meanwhile, when we take the limit, we don't get approximate anymore. What we're going to get is zx, and times xu, that's the partial derivative of x with respect to u, plus zy, times the partial derivative of y with respect to u, like that. And so we get a formula for the partial derivative of a function that actually has functions plugged into it. Now for a quick example, let's just make up something quick. How about just z equals, how about x squared plus y cubed? And then x, how about just something like 2u plus 3v? And then y equals, how about u squared times 3 to the v, like that. Now if I want the partial derivative of z with respect to u, I just need to start plugging in stuff. So here we go. Partial derivative of z with respect to u is zx, well that's just 2x, times xu, well that's just 2, plus zy, well that's just 3y squared, times yu, that's going to be 2u, 3 to the v. And you can see we don't actually try to plug those other functions back in, because when we do more layers it's going to get a lot worse. And if we are given data, which in real life that's what we're given, plugging back, it's not even possible to plug in because we don't actually have formulas for it. Meanwhile, we do now have a formula for taking the partial derivative of a function with respect to one layer.